Good morning viewers, welcome to my YouTube videos on high physics norms.
Hello, good morning students. Today our topic is properties of matter in solids. Solids topic, properties of matter. Now generally in this topic, if you take a solid, say for example I am considering a cuboid. Let us say this is a cuboid which is having the length, breadth, this is the length, breadth and height. If you apply some stress on it, so initially it is hanging to a rigid support. If you apply some weight here, automatically it will be elongated like this. That means the elongation should be in three ways. In general we can say one is lengthwise increasing, another is breadthwise increasing, another is heightwise increasing. So increasing or decreasing, changing, length changing, breadth changing, height changing. Say for example lengthwise increasing, which we can call as a longitudinal expansion, or we can say linear expansion. If it is a breadthwise, means breadthwise expansion. So if you consider these two, length and breadth, which we can call area. So as you know that length into breadth is nothing but the area. We can say that areal expansion, we can say, or we can say this in this topic we can say this is sharing expansion, we can say. Another is length into breadth into height, length into breadth into height, which indicates the volume. So as you know that volume is equal to length into breadth into height, which you can say that the volume will be expanded. That means volume expansion. That means it will having three types of expansions: linear expansion, aerial, or we can say sharing expansion, and another is volume expansion, we can say. That may be compression or expansion. In general, if weight is attached, means automatically it will be expanded. We can say the volume will be expanded. Three types of expansions we can say. Before going to discuss about this, the main formula, that is a main definition, main topic here is Hooke's law. We can say Hooke's law. How can you define a Hooke's law? So Hooke's law. In this, new terms will come. In this particular area, if you apply some force, which we can call as stress, we can say. If it is elongation is there, that means strain will be present. So stress and strain, these are the two new terms in this chapter. So we can say that Hooke's law give the definition of stress and relation between stress and strain. So we can say the definition of simple Hooke's law is within elastic limit. This is important. Within is the important here. Within the elastic limit, stress is directly proportional to strain. We can write it mathematically: stress proportional to strain. So to remove the proportionality, a constant is introduced, which we can call as we can say sigma, or E, we can say E into strain. So E is nothing but the modulus of elasticity. So modulus of elasticity, E is equal to, simply we can say, stress by strain. So this is the basic definition of Hooke's law. So we can draw that graph also for this. Here is a graph. So generally strain on the x-axis, stress on the y-axis. It will give the directly proportional, in the sense a straight line passing through the origin. This is the relation between stress and strain, which can be explained by the Hooke's law. Now our next topic is what is a stress. How many types of stress are present here? So first of all, what is a stress? Stress means what? So this is the simple definition. The internal restoring force per unit area of cross section of the deformed body is called stress. That means if you take a body, that is a string, let us say this is a string, okay, uniform wire, simply we can say, okay, which is suspended to the rigid support. Now at the end of this rigid support, if a weight is attached to this, automatically what happened, the wire will be elongated a little bit, like this, let us say. That means the length of the wire will be increasing here by applying the stress here in this particular area. Then automatically it will be elongated like this. How much it will elongated? That is E, you can say. This is elongation, you can say. Now in this particular area, some force is attached to this. Automatically the shape of the wire will be changed, which we can known as deformation. Deform means changing of the shape. So simply the definition of stress is the internal restoring force. The internal restoring force per unit area of cross section of the deformed body is called stress, or simply it can be represented mathematically. You can write stress is equal to simply restoring force by area of cross section. Now the units, as usual, you know that force unit is Newton per area meter square, that is Newton per meter square, or another units is Pascal, PA. So we can know the dimension formula also. So dimension formula is force means mlt power minus 2 by area means length into length, L square, what you will get, ml power minus 1 t power minus 2, that is 1. This is the dimension formula of the stress. Now how many types of stress are there? So in this particular wire or rod, if a force is applied normally, then it is called tensile stress. This is also known as a longitudinal stress also. If it is compressed, then we can say that is a compressive stress. Say in case of a bulk solid or liquid or a gas, if the deforming force is applied normally to such surface, the magnitude of force of any small area is proportional to the area, then the stress is called volumetric stress. So these are the types of stresses. Similarly, strain. What do you mean by the strain? Strain. So which is the simply definition? It is the ratio of change in a dimension to original dimension. Change in dimension to original dimension. So the dimension will be either is a lengthwise expansion or lengthwise changing or sharing wise changing, or you can say volume wise changing. Simply the basic definition is change in dimension to original dimension. That means both are same. That means it will have no units. No units means as usual no dimensions also. So this is about the state. Now we are going to discuss about the types of stresses and the types of strain and what is the relation between them in a single view. Now types. First is longitudinal, we can say. Longitudinal, that is lengthwise. Say this is longitudinal stress. So what is the definition? Simple definition. That is a force, restoring force by area of cross section as usual. Same formula. What is the longitudinal strain? So this is a simple definition. Change in length by original length. That is simply mathematical. You can write change in length is delta L by R, or you can say elongation by length. This is the formula for the longitudinal strain. This is very important. So in this will be written in the mathematical. You can say that F by A, force by area. This is about the longitudinal. And then longitudinal. How can you get the relation between these two, longitudinal stress and a longitudinal strain? That can be given by the Young's modulus. Simply the Young's modulus. So Young's modulus represents by symbol of Y. How can you define the Young's modulus? You can say that this is the ratio of longitudinal stress to the longitudinal strain. So it is the ratio of longitudinal stress to longitudinal strain. So mathematical part is important. Mathematically you can say F by A by E by L. Now you can say FL by A. This is a general formula. In sometimes you can use in place of force, weight will be acting. Those you can say mgl by area, means as usual if you take a wire, pi r square into E. So in general we can get the for doing the problem. So in so many problems they will ask the elongation. That's why I want to bring the relation for this elongation. So E is equal to, you can say, mgl by pi r square y. This is the formula. Or simply you can say E is proportional to L by R square. If force and Y are constant, then you can use this formula. If volume is constant, that means you can use the formula. If volume is constant, then you can use E is proportional to L square. That is simply double action. E1 by E2 is equal to L1 square by L2 square. So in this way, we can use the formulas for the Young's modulus point of view. We can go depth after completing this topic. We can explain. We can use this Young's modulus in the thermal properties of solids also. So up to this, okay, for the competitive point of view. So this is about the longitudinal one. Okay. Next will be shearing. Shearing means, so here two types of shearing are shearing stress and shearing strain. So you can say shearing stress. So as usual the formula is same, which is nothing but the force by area, F by A, direct formula I am writing. So how we can explain the shearing? Say for example, if you take a rectangular box like this, so that means now this is a rectangular box. Let us say if you apply some force on this, F force apply on this, automatically the shape of the box will be changed to like this. This is looking like a parallelogram. That means the elongation should be, we can say theta. Theta this side bending. That means here is also theta. That means applying same force here, but the force will be shared in the both sides. Say this is for example delta x, you can say. So this is some actual length is, you can say, x. The sharing will be delta x. This is also delta x. That means this is a F force applying on single place, that is at this point it will be shared like this. Delta x will be the change, x is the original value. That means we can say the definition of shearing strain. Simply we can say the definition, the formula is a change in angle. We can say simply theta, or you can say simply delta x by x. So shearing strain is nothing but theta, or you can say change in dimension by original dimension. So we can get this in between these two, a relation we will get here like this. That is represented with the rigidity modulus. Rigidity modulus. The symbol for the rigidity modulus will be like this, neta. So how can we define this rigidity modulus? It is simply, it is the ratio of shearing stress to the shearing strain. Shearing stress to shearing strain. Or you can say mathematically simply F by A by theta. Or you can say F by A by delta x by x. Simply eta is equal to F by A theta or Fx by A into delta x, depending on the situation we can explain this. So this is about the rigidity modulus represented by neta symbol. This is longitudinal, shearing, and then finally volume. That is volume wise. Volume, or you can say bulk. So how can I define this? Same formula here. This is volume stress. So simply force by area, F by A. In this particular case, we can use pressure. So there we can say pressure. That is P, which is nothing but the force by area. Shearing. Shearing means same volume strain. So same thing happen here. If you take a object, if it is applied throughout the body with this particular force, automatically the shape will be decreased generally. That means volume will be decreased. So decreasing in the sense we can represent with the negative symbol, or simply the definition of volume strain is ratio of change in volume to initial volume. Okay, that means mathematically you can write delta V by V. Before that you can put the minus value. Negative indicates the decrease in the volume. So this is about the volume stress, this is about the volume strain. So we can get the relation between volume stress and volume strain with the help of the bulk modulus, we can say. This is bulk modulus, represented by the symbol of K. So how can we define this? You can say this simply, it is the ratio of volume stress to volume strain. So you can write it mathematically. K is equal to volume stress is nothing but you can use the volume pressure by volume strain is nothing but minus delta V by V, or simply you can write PV by delta V. You can put minus here. Okay, this is about the volume stress, volume bulk modulus. If you observe these three, Young's modulus, rigidity modulus, bulk modulus, in all the cases numerator is force by area, force by area is also pressure is nothing but force by area, whereas the denominator is strain, 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 all the different types of strain. That means strain have no units as usual, no, that is force by area unit, that is nothing but these Young's modulus, rigidity modulus, bulk modulus, three have same units and dimensions. So simply we can say that y comma eta and k have same units and dimension formula. That is simply Newton by meter square or Newton per meter square. And as usual, the dimension formula is previously wrote m L power minus 1 T power minus 2. This is about the y, n and k. So after this, total stress and strain relation between them will be in a single page. You can take a snapshot also. Next, continuation to this, the relations between y, n and k. Another small thing is the Poisson's ratio is there, and some more small topics are there. We'll continue this. Here another thing is compressibility. Represented by the C. So simple definition of the compressibility is a reciprocal of bulk modulus. You can say the reciprocal of bulk modulus. Or you can write it mathematically, C is equal to 1 by K, or simply minus delta V by PV is the formula. Units as usual reverse. Units will be like this. Newton power minus 1 meter square. Reverse. As usual dimension formula, you can check it. And then later, another thing is Poisson's ratio. It is also small definition. Poisson, the first is ratio, represented by the symbol of sigma in general. So we can say the definition of this one will be, it is a ratio of lateral strain to the longitudinal strain. It is the ratio of longitudinal strain, both are strain only, ratio strain to lateral strain. So mathematically you can write it, longitudinal means delta L by L, lateral means delta B by B breadthwise, or simply we can say from this, lateral strain delta B by B is equal to sigma into longitudinal strain. This is a formula. So it will have no units. Why? Because both are same only terms. Strain is strain also no units. That means strain by strain is no units only. So Poisson's solution is, this value will be theoretical value. Theoretical limits. Theoretical means which will be assumed. Theoretical limits is minus 1 to 0.5. So practical limits. Practical limits will be 0 to 0.5. In some books, you can say 0.2 to 0.4. So both are correct. This is about the Poisson's ratio. Now the relation between, if the volume strain is given, we can get the relation for this will be now the relation between volume strain and Poisson's ratio is in generally we can say the formula will be like this. Volume strain delta V by V, which is equal to delta L by L into 1 plus 2 sigma. This is the relation between volume strain and longitudinal strain and Poisson's ratio. This is very important formula which will be used in doing the problems, and some more about this will be relations between, so relation between exomodulus, bulk modulus, rigidity modulus and Poisson's ratio. So the first relation will be exomodulus, y is equal to 2 eta into 1 plus sigma. Another relation is, you can write y is equal to 3k into 1 minus 2 sigma. Exomodulus relation. In general, this relation, if you remember, means it can be easily derive all the relations. So that is 9 by y is equal to 3 by eta plus 1 by k. This is important. Y and k relation. Simple. Or you can use the calculation by doing the LCM. We will get y is equal to 9k eta. by eta plus 3k. Some more another relation for the sigma is also there. That is sigma is equal to, that is Poisson's ratio is equal to 3k minus 2 eta by 6k plus 2 eta. This is another relation. So these are the relations between the Young's modulus, bulk modulus, rigidity modulus, and Poisson's ratio. These are the very important relations. Derivation for the strain energy. So first of all, how will you define the strain energy? As usual, we know that the definitions previously kinetic energy, potential energy. In the similar way, I try to write that strain energy. That is, we can say simply strain energy means energy possessed by a body by virtue of its deformation. That is about the strain energy. Mathematically, you can write strain energy U is equal to half into stress into strain into volume. This is general formula for the strain energy. So how can you derive this strain energy? For this explanation, I am considering a string which is suspended to the rigid support. Initially, there is no force applying on it. We can say that F1 is equal to 0. If you apply some force on this wire, F2 is equal to F, you will get the wire will be elongated. Let us say zoom it. Actually, this much elongation is not possible. So if it is, so I am zooming this for our consideration. So this will be elongation. Say for example, E, expansion will be there. Now, if it is elongated means work should be done here. That means we can say that during elongation, work done is equal to average force into displacement. That is elongation. So, work done is equal to average force into elongation. So, you can write it W is equal to average force means F1 plus F2 by 2 into elongation means E. So, I'm writing once again, that is 0 plus F by 2 into E, or simply you can say W is equal to half Fe. So this is a formula for the work done during the elongation, half Fe. So mathematically, here work is stored in the form of strain energy. You can say that here work stored in the form of strain energy. That is U. Simply you can write U is equal to half into F into E. For my convenience to get the relation, I am multiplying and dividing with the volume here. Volume by volume. So as you know that some more 1 by 2 into F into E into, here in place of volume I can write area into length into volume as usual. But we know that force by area indication stress, elongation by original length indication strain. So simply you can write U is equal to 1 by 2 into stress into strain into volume. Simple derivation. In some questions they will ask strain energy per unit volume. If they ask strain energy per unit volume, that is you can say U by V, which is equal to half into stress into strain. You can apply the formula for the Young's modulus also here. As you know that Young's modulus is equal to stress by strain. Or simply you can say that stress is equal to Y into strain. Or you can say strain is equal to stress by Young's modulus. You can apply the formulas here. You will get U by V is equal to 1 by 2 into, in place of stress if you apply the strain, you will get Y into strain, that is strain square. This is one formula. Another, if you apply this, you will get U by V, that is strain energy per unit volume, 1 by 2 into, in place of strain, if you apply stress by Y, you can say that simply stress into stress by Y, that is stress square by Y. This is also another important formula. So these are useful for doing the problems. This is about the properties of matter in a brief view. Thank you for watching.